watched? No, I just watched another movie with Matt Damon. I'm trying to remember what it was. Yes, I just rewatched that this weekend, yeah. Hi there. Welcome to Introductory Algebra at Portland Community College. I'm Ann Sittimer, and this is Candace Kling and Steve Simons. You'll be seeing a lot of us during this telecourse. You'll probably see us more than you'll see your instructor. Teaching math in a television studio has been a new experience for us. We're used to being in the classroom with students. But over time, teaching math through a television camera has gotten easier. I mention this because some of you will find algebra new and different at first. Yet we know that algebra will become familiar to you in the same way as teaching algebra in this new setting has become familiar to us. Candace, Steve, and I will present one part of each lesson. Here in the studio, we've got this desk with a computer. If I'm presenting my part of the lesson, I'll be at the desk. Usually Steve is in the studio with me, and Candace is in the control room with the producers. They're making sure I don't make any arithmetic mistakes on TV. The examples I will be working show up on this computer monitor, and through the miracle of television, you will see these examples behind me, where the blue curtain is now. This monitor allows us to write our solutions directly on it, so you'll see us work through a problem solution as we discuss the strategy. Let's see what this all will look like.
Congratulations on taking the first step on an independent learning journey. There are several materials you need for success in this class. You need to rent or record the lessons. Additionally, you'll need to purchase the telecourse packet, the textbook, a ruler, a scientific calculator, and graph paper. The telecourse packet includes a syllabus with contact information for your instructor, a schedule for the course, homework assignments, testing information, resources for help with the material, and other information your instructor feels will help you succeed in the course. The actual instructor of the course changes from term to term. Information about the instructor can be found in the course syllabus. Your instructor will be administering and grading your tests and other assignments. Your instructor is also available for help with the materials. If you have not yet registered, please visit www.pcc.edu and follow the appropriate links for registration information.
As in all things in life, your chances for success in this course are greatly improved if you keep a positive attitude about the class. Math can be really frustrating at times, so it's sometimes difficult to keep a positive attitude. It will help you if you keep in mind that everyone struggles with math from time to time. It also really helps if you remember that it's not only okay to get help when you need it, it's a really good thing to get help when you need it. Another thing that helps is if you keep your materials organized. Find a strategy that allows you to easily find your notes, homework, and other important course materials. You need to make sure that you actively watch the lessons. For one thing, you need to have your notebook and a pencil ready for action while watching the lessons. When you watch us write the solution to an example, you want to pay attention and copy not only the answer, but the entire solution process. We consistently show the steps and organizational strategies that you should follow when writing your solutions. You want to budget more than 3 hours per week for watching the lessons. While watching the lessons, you want to actively work the examples along with us. You should sometimes even freeze the video before or after we work an example and try working the example yourself. This can help you identify whether or not you really understand what is being illustrated. It helps a whole lot if you read the relevant section of your textbook before watching the lesson. While you're reading, you should even try working the examples in the text. Now, having said that, it's important that you cut yourself some slack if you don't understand an example. If nothing else, your attempt to work the problem will help you identify important information in the videotape lesson that you might not have recognized as important without considering the material ahead of time.
This might sound obvious, but you need to do your homework. One thing that will help keep you on task is an established schedule that you can stick with. You should budget 8 to 12 hours of study time per week, above and beyond the time you spend watching the telecourse lessons. You need to do your homework regardless of how well you understand the lesson. Working your homework assignments is the most important part of the learning process. Genuine understanding of the material frequently doesn't even begin until you've attempted some problems. Even making mistakes is part of the learning process, and working through the mistakes ultimately leads to greater understanding. Sometimes you'll need help to work through the mistakes. If you find yourself really frustrated, it might be a good idea to take a break. Everybody gets frustrated at times. The best way to get past the frustration is to get some individual help. There are all sorts of people at PCC who are available to help you be successful. Please take advantage of this help when you need it. The clearest sign that you really understand the material is being able to work problems without looking at examples. It's a great strategy to look at examples when you are first working problems, but you need to get to the point where you can work the problems without looking at examples.
I've encountered many students in the classroom who've clearly put in their study time, completed all of the homework successfully, but still end up not doing well on the test. We certainly don't want this to happen to you, so let's talk about some of the obstacles and some of the things you can do to overcome them. If you are in the habit of keeping up with your homework, that's great. Doing your homework on a regular basis is the most important preparation for taking a test. It's also important to memorize key definitions, facts, and strategies. Many students find flashcards useful for this. It's a really good idea to create practice tests. Copy onto a piece of paper a representative sample of problems from each section of the book that will be covered on the test. Make sure you mix up the problems and include the types of problems that are most difficult for you. On another day, sit down and work the problems without looking at any notes or the textbook. Try timing yourself as if you were actually taking the test. An added bonus of a practice test is that it will help you identify the types of problems you need to spend a bit more time practicing. Now the real test. The most important thing is to relax. When I get exam, before I even look at it, I take a few deep breaths and remind myself that I'm capable of doing well. When starting the test, it's important to read the directions and each problem before you start to work any problems. Work the problems that seem quick and easy first. Then go back and work the problems that require more time. Watch your time and pace yourself. This is a lot easier to do if you started with the problems that are quick to solve. If you get stuck while working on a problem, stop and try working on another problem. Return to the problem that stumped you later. Finally, when you finish a problem, particularly an application, make sure you answer the question asked. Always check your work. Throughout these lessons, Steve, Candace, and I will show you many strategies for checking your work. This may sound like a lot, but when you're preparing for a test, you can practice some of these test-taking strategies. Taking tests well is a skill you can practice just like any other skill.
A lot of people feel that they just can't learn math. That's not the best attitude when you're trying to pass a math class. We can't promise you that it will be easy to learn the math, but we know that you can be successful. It's really important that you know and feel that you can be successful too.
A lot of people even say that they hate math. It's really tough to learn about something that you hate. It helps a lot if you look for the things you like about the subject. We've tried to present the material from a variety of perspectives so that everyone watching the series can find things they relate to. We've worked as a team to develop consistency, but have also maintained some individuality to allow you exposure to different perspectives.
Ultimately, the most important person in this course is you. With proper preparation, a positive attitude, a good work ethic, and a willingness to seek out additional help when needed, you will be poised to succeed in this and any other math class you choose to take. I'm going to turn it over to Candace now so that we can get started on the math.
For our first lesson in Math 65, we're going to look at systems of linear equations in two variables. Following me, Steve's going to look at the substitution method, and then Anne is going to look at some types of solutions to these systems. I'm going to start by looking at an application of a system of linear equations. Then I'm going to talk about what it means to be a solution to a system of linear equations in two variables. And I'm going to end with several examples of solving systems of linear equations by graphing. So let's start with an application of a system of linear equations. At the same instant a Cessna takes off, a Boeing 747 is descending from an altitude of 450 feet. If y equals 50x is the height in feet of the Cessna x seconds after takeoff, and y equals negative 25x plus 450 is the height of the Boeing 747, also in feet, x seconds after the Cessna takes off, at what time will the two planes be at the same altitude, and what is that altitude? So let's take a look at the graph of these two equations. Both of these were linear equations, so when we graph them, we should see two lines. The Cessna was taking off, so our increasing line on this graph represents the height of the Cessna. The Boeing 747 is descending from a height of 450 feet, so we see our vertical intercept at 0,450, and the line is decreasing. We're interested in when is the height of these two planes, or the altitude of these two planes, the same. Well, looking at the graph, the only time that the altitude of the two planes is the same is right here at 300 feet. And if we look down to our time axis, that occurs at 6 seconds. The ordered pair 6, 300, tells us this. So we can say that 6 seconds after the Cessna takes off, both planes are at an altitude of 300 feet. So let's look a little bit more at systems of linear equations in two variables. You should remember from Math 60 that a linear equation in two variables, ax plus by equals c, graphs to a line, with the condition that a and b cannot both equal 0. So we just looked at an example of two different linear equations, both of which graph to a line, in our airplane example. A system of linear equations consists of two or more linear equations. We're going to focus on solving systems of linear equations containing two equations in two variables. We'll often refer to these as two equations in two unknowns. Our airplane example was a system of linear equations. We had two linear equations representing the altitude of the Cessna and the altitude of the 747 airplane. And we had two variables. In this example, we used the variables x and y. So what is the solution to a system of linear equations in two variables? Well, in our first example here, we're asked to determine if 3, negative 2 is a solution to the system 3x minus y equals 11 and x plus 2y equals 1. Well, a solution to a system of two equations in two variables is an ordered pair that is the solution to both equations in the system. So what we need to do is take the ordered pair 3, negative 2 and make sure it's a solution to both of the equations in the system. So if we let x equal 3 and y equal negative 2, then looking at our first equation, the left-hand side, 3x minus y, becomes 3 times 3 minus negative 2. That's 9 minus negative 2, which is the same as 9 plus 2, which is 11. Good, that's what we wanted. Look at our first equation. We wanted 3x minus y to equal 11. What about our second equation? Well, looking at the left-hand side, x plus 2y becomes 3 plus 2 times negative 2, which is 3 plus negative 4, which is negative 1. Look back at our second equation. What we wanted was x plus 2y to equal positive 1. So this doesn't satisfy the second equation. In order to be a solution to a system of equations, the ordered pair has to satisfy both equations. Since the ordered pair 3, negative 2 doesn't satisfy the second equation, 3, negative 2 is not a solution to the system. So we can go ahead and say that no, the ordered pair 3, negative 2 is not a solution to this system of equations. Let's look at another example. This time we're asked, is 3, negative 3 a solution to the system 3x minus y equals 12 and x plus 2y equals negative 3? So this time we're letting x be positive 3 and y be negative 3. So then if we focus on the first equation, looking at the left-hand side, 3x minus y would be 3 times 3 minus negative 3. That's 9 minus negative 3, which is the same as 9 plus 3, which is 12. That checks. We wanted 3x minus y to equal 12. What about the second equation? Well, focusing on the left-hand side, we have x plus 2y. That would be 3 plus 2 times negative 3. That's 3 plus negative 6, which is negative 3. And look at our second equation. We want x plus 2y to equal negative 3. So this checks also. 3 negative 3 is a solution to both of the equations, so 3 negative 3 is a solution to the system. So we can go ahead and answer the question and say yes, the ordered pair 3 negative 3 is a solution to this system of equations. One more example of this type. Is 5 negative 1 a solution to the system x minus y equals 10 and x plus 4y equals 1? Well, this time, if x is 5 and y is negative 1, then looking at our first equation, the left-hand side, x minus y, would become 5 minus negative 1. That's the same as 5 plus 1, which is 6. But we want x minus y to equal 10. So this does not satisfy the first equation. 5 negative 1 is not a solution to the first equation. We don't even need to check the second equation. If we substituted 5 for x and negative 1 for y, we would see that the left-hand side of the second equation does simplify to 1, but it doesn't matter. Our ordered pair is not a solution to the first equation, so it's not a solution to the system of equations. So we can go ahead and answer our question and say no, 5 negative 1 is not a solution to the system of equations. Well, here we have a graph with a couple of lines. Notice that the line labeled line 1 is increasing and the line labeled line 2 is decreasing. The first thing that we're asked in these fill-in-the-blank type questions is to find an equation for line 1. So if we think about slope-intercept form, y equals mx plus b, what I need to do is find out what's m and what's b. Well, b comes from the y-intercept. Looking at line 1, our increasing line, the y-intercept is 0, 1. That tells me that b equals 1. Now the only thing I need to find is m, which represents the slope of the line. So if I locate another point on the line, say the point negative 1, 0, our x-intercept, to get from the x-intercept to the y-intercept, I need to go up 1 and then right 1. So the slope m, which is rise over run, is 1 over 1, which is 1. So for our equation of the line, we can write y equals 1x, I can just write x, plus b, and b I found to be 1, since the y-intercept is 0, 1. Well, what about an equation for line 2? In line 2, immediately I can see the y-intercept, that's 0, 4. So that tells me in line 2, b is equal to 4. Now I still need the slope. I need to find the value of m. So looking for a second point on the line, here's one at negative 2, 5. To get from the point negative 2, 5 to the y-intercept, this time I would have to move down 1. So thinking about the slope, rise over run, the rise is going to be negative 1 since I moved down 1, and right 2. So the run is 2. The slope is negative 1/2. So an equation for line 2 is y equals negative 1/2 x plus b, which I found to be 4. So negative 1/2 x plus 4. Next, I'm asked about the point of intersection of the two lines. Well, let's remember that every point on the line is a solution to the equation, and every solution to the equation lies on the line. So the only point that satisfies both equations is the point that lies on both lines. That's what we're looking for here, the point of intersection. So looking at where our two lines intersect, it looks like they intersect at the point 2, 3. So to fill in the blank here, the point of intersection of the two lines is the ordered pair 2, 3. The solution then to the system, y equals x plus 1, that's line 1, and y equals negative 1/2 x plus 4, that's line 2, is the ordered pair that we just found, 2, 3. The point where the two graphs intersect is the solution to the system of equations. So now let's look at several examples of solving systems of linear equations by graphing. So in this first example, we're going to solve the system y equals 3x plus 1 and y equals 1/2 x minus 4. Both of these lines are in slope-intercept form. I'll use that to graph them. Starting with the first line, since b is 1, I know that the y-intercept is 0, 1. And since m is 3, I know the slope is 3. I can think of this as the fraction 3 over 1. So my rise over run is 3 over 1. So starting at my y-intercept, I can go up 3, right 1. Up 3, right 1. But I can also think of 3 as the fraction negative 3 over negative 1. So I could have started at my y-intercept and went down 3 and to the left 1. All of these points lie on the same line. So I'm going to get out my straight edge to graph these, and I'm going to be very careful about graphing them because to solve this system, I want to know what the point of intersection between the two lines is. So graphing this line, we see that we have an increasing line, which makes sense because the slope is positive. Now let's graph the second line. b is negative 4, so my y-intercept is 0, negative 4. The slope is 1/2. So starting at my y-intercept, I can go up 1, right 2. Up 1, right 2. And find several points on the line. Again, I'm going to take out my straight edge and carefully sketch this graph. So I'm looking for the point of intersection between these two lines. Looking at my graph, it looks like the two lines intersect at the point negative 2, negative 5. But I want to check to make sure that this ordered pair really does solve the system. So my proposed solution was negative 2, negative 5. Let's see if this satisfies both of the equations. If x equals negative 2 and y equals negative 5, then, starting with our first equation, I'm going to focus on the right-hand side where there's some arithmetic. I have 3x plus 1. That would be 3 times negative 2 plus 1. That's negative 6 plus 1, which is negative 5. This is good. I wanted y to equal negative 5. So this checks. I also need to check to make sure that the ordered pair satisfies the second equation. So in the second equation, again, I'm going to focus on the right-hand side where there's some arithmetic. I have 1/2 x minus 4. So this would be 1/2 of negative 2 minus 4. Half of negative 2 is negative 1, and when I subtract 4 from negative 1, I get negative 5. Again, this is good. We wanted y to be negative 5. Before I go on, though, now that I've checked my solution, I want to make sure that I state the conclusion. So my conclusion would just be that the solution to the system is negative 2, negative 5. Let's look at another example. In this one, we're asked to solve the system y equals negative 2x plus 3 and x minus 2y equals 4. This time my first equation is in slope-intercept form, but my second equation is in standard form. Starting with the first equation, I can plot my y-intercept, 0, 3, and use my slope, negative 2, to find some more points on the line. So negative 2 I can think of in fractional form as negative 2 over 1. Starting at the y-intercept, I'll go down 2, right 1. And I can do that several times to find several points on the line. Getting out my straight edge again, I want to carefully sketch this line. Now the second equation I said was in standard form, x minus 2y equals 4. I could put this in slope-intercept form by solving for y, and that would tell me the y-intercept and the slope to make it easy to graph. But looking at this equation, it looks like it's pretty easy to find some points that would be on this line. For instance, if I wanted to find the x-intercept, I would set y equal to 0. If I set y equal to 0, my equation becomes x equals 4. So I know the x value has to be 4. If I want to find the y-intercept, I would set x to 0. If I let x equal 0, the equation becomes negative 2y equals 4. So what do I have to multiply by negative 2 to get 4? Negative 2. Negative 2 times negative 2 is 4. So the y-coordinate of the y-intercept is negative 2. Well, let's plot those 2 points. I have the point 4, 0 for my x-intercept and the point 0, negative 2 for the y-intercept. Once I have 2 points on a line, I can determine the slope. If I start at the y-intercept 0, negative 2 and move to the x-intercept, I would have to move up to right 4. So the slope is 2/4, or 1/2. I can also think of 1/2 as negative 1 over negative 2. A negative divided by a negative is a positive. So I could start at the y-intercept and move down 1, left 2, down 1, left 2, and find several other points on the line. So again, with my straight edge, I'm going to carefully sketch this line. Now looking at the 2 lines, it looks like they intersect at the point 2, negative 1. Again, I want to check to make sure that this really is the solution to the system. So I'm going to take my proposed solution of 2, negative 1 and look at both of the equations in the system and make sure that this ordered pair satisfies both. So if x is 2 and y is negative 1, then starting with the first equation, and I'm going to start with the right-hand side where there's some arithmetic, I have negative 2x plus 3. That would be negative 2 times 2 plus 3. That's negative 4 plus 3, which is negative 1. That's what we wanted y to be, so this checks. What about the second equation? Well, in the second equation, I'm going to focus on the left-hand side where both the variables are. X minus 2y would be 2 minus 2 times negative 1, which is 2 plus 2, which is 4. Looking back to our second equation, we wanted x minus 2y to equal 4. So this checks. So I saw on the graph the ordered pair 2, negative 1 was where the 2 lines intersected, and I've just checked that this ordered pair really does satisfy both of the equations. So I'm going to go ahead and state my conclusion and say the solution to the system of equations is this ordered pair we just found, 2, negative 1. Now let's solve the system y equals negative 2x plus 5 and x equals 4. The first equation is in slope-intercept form, so I'm going to start by plotting the y-intercept, 0, 5. Then I have a slope of negative 2. I can think of this as the fraction negative 2 over 1. So starting at the y-intercept, I'll go down 2, right 1, down 2, right 1. And I can do that several times to find several points on the line. Getting out my straight edge, I want to carefully graph this line. Now my second equation looks a little odd. X equals 4. There's not even a y in this equation. You might remember from Math 60 that an equation like this, an equation of the form x equals a constant, always graphs to a vertical line. Well, let's think about it. The x-intercept would be 4, 0. In this point, the x value is 4. It satisfies the equation. Then we want to think about all of the other points in the coordinate plane where x is equal to 4. there's lots of them. Any of the ordered pairs where x is equal to 4, though, are going to lie on the same vertical line. So using my straight edge to sketch the vertical line, x equals 4, we see that our two lines intersect at the point 4, -3. Well, this definitely makes sense for the second equation. The x-coordinate of this ordered pair is 4, and the second equation says x has to equal 4. Well, what about the first equation? Well, there's actually a couple of things I can think about here. If I hadn't even graphed these and I looked at these two equations and saw in the second equation all that I have is x equals 4, I could have just taken this 4 and substituted it in place of x in the first equation. Let's try that and see what y ends up being. So if x equals 4, then we're working with the equation y equals -2x plus 5. So that would equal -2 times 4 plus 5. That's -8 plus 5, which is -3. Well, look at our ordered pair. In our ordered pair, we saw 4, -3. The y value was -3. So this does check. So we can go ahead and write our solution, that is, the solution to the system of equations is this ordered pair we just found, 4, -3. And we actually found that in two different ways. Remember, the first thing we did was graph it, but then we also substituted 4 into the first equation, since our second equation was just x equals 4. Let's look at another example. Here we're asked to solve the system y equals 3x minus 5 and y equals 3. The first equation, again, is in slope-intercept form, so I'm going to start with my y-intercept of 0, -5, and use my slope of 3. I can think of 3 as the fraction 3 over 1. So from my y-intercept, I'll move up 3, right 1. And I can do this several times to find several points on this line. Getting out my straight edge, I'll carefully sketch this line. My second equation is y equals 3. Again, this might be something you remember from Math 60. When you have an equation of the form y equals a constant, this is always going to graph to a horizontal line. Let's think about this. If y equals 3, well, one place y equals 3 is right on the y-intercept, 0, 3. What about other points in the line where y is equal to 3? There's lots of them. But any of these points are going to lie on the same horizontal line. So let's draw our horizontal line, y equals 3. To solve the system, I'm looking for the point of intersection of these two graphs. Looking at this point here, well, there's an obvious coordinate of the point. The y-coordinate is 3. But what about the x-coordinate? Even though I carefully graphed these lines to help me find the point of intersection, it looks like the x-coordinate is not an integer value. It looks like it's somewhere between 2 and 3. Well, let's think about what we did with the last system. Our second equation's a little bit easier to work with. Y is equal to 3. So what if I take that value 3 and substitute it for y in the first equation? So if y equals 3, then what do we have for that first equation? 3 equals 3x minus 5. Now, solving this for x, the first thing I would do is add 5 to both sides of the equation. That gives me 8 equals 3x. And to completely isolate x, I'll divide both sides of the equation by 3. That gives me 8/3 equals x. Now let's look back at the graph and see if this makes sense. So I just found that 8/3 is equal to x, or we can also say x is equal to 8/3. On our graph at the point of intersection, remember I said it looked like the point of intersection had an x-coordinate between 2 and 3. It even looks like that x-coordinate is closer to 3. Well, 8/3 is 2 and 2/3. That's definitely between 2 and 3, a little bit closer to 3. So this does make sense with our graph that the x-coordinate is 8/3. So I can go ahead and write my conclusion. The solution to the system of equations is 8/3, 3. Well, now let's solve the system y equals -5, x equals 2. This time we have a horizontal line through the y-intercept 0, -5, and a vertical line through the x-intercept 2, 0. So let's go ahead and graph these. My horizontal line goes through the point 0, -5. And my vertical line goes through the point 2, 0. Where do these two lines intersect? Well, let's look at the point here where x is 2 and y is -5. You might have predicted the solution before I even graphed the lines. Look at our equations. Y always has to be -5, x always has to be 2. The only point at which these two lines are going to intersect is the point where x is 2 and y is -5. So our solution makes sense. So the solution to the system of equations is 2, -5. Well, let's look at one more example. Here we're asked to solve the system y equals 2x minus 1 and 2x plus 3y equals 4. Starting with that first equation, we have an equation in slope-intercept form. So I'll plot the y-intercept, 0, -1, and using my slope of 2, from the y-intercept I can go up 2, right 1, up 2, right 1, several times to get several points on the line. And then I'm going to use my straight edge to carefully sketch this line. Whenever I'm solving a system of equations graphically, I want to be very careful about graphing my line because I know I'm looking for the point of intersection between the two lines. Now the second equation, 2x plus 3y equals 4, is given in standard form. I can find the x-intercept pretty quickly by letting y equal 0. If y is 0, I'm left with 2x equals 4, so x has to be 2. The y-intercept's a little bit more difficult to find, so I think I'm going to go ahead and take this equation, 2x plus 3y equals 4, and put it in slope-intercept form. To do that, I'll just solve the equation for y. So I'm going to subtract 2x from both sides of the equation. That gives me 3y equals 4 minus 2x. And then I'm going to divide both sides of the equation by 3. Remembering that means I have to divide every term by 3. So on the right I have 4 divided by 3 minus 2x divided by 3. Now I have an equation in slope-intercept form. The slope is -2/3. The y-intercept is the point 0, 4/3. That's why in standard form it was a little bit hard to find the y-intercept. I do know a point on the line though. I wrote the ordered pair 2, 0. That's my x-intercept. So I'm going to start from my x-intercept 2, 0 and use my slope -2/3. So starting at 2, 0, -2/3, well, if we think of this as -2 over +3, I would move down to right 3. If I do that again, I'm going to be off the grid, but I can also think of the fraction -2/3 as +2 over -3. So starting at the x-intercept, I'm going to go up 2 and to the left 3. And I can do that a couple of times. And then using my straight edge to carefully sketch this line, I need to look for the point of intersection between these two lines. Looking at the graph here, it doesn't look like this point of intersection lies on integer coordinates. It looks like the x value and y value are kind of close to 1. And if I think about the ordered pair 1, 1, well, in the first equation, if y is 1 and x is 1, The right-hand side is 2 times 1 minus 1, which is 1. That does give me a y value of 1. So 1, 1 is a point that satisfies the first equation. But if I put 1, 1 in the second equation, 1 for x and 1 for y, the left-hand side is 2 plus 3, which is 5, not 4. So I know 1, 1 doesn't satisfy both of the equations. Using graphs to solve a system of equations is quite helpful in that visually it shows you what's going on. But if you don't have integer coordinates for the solutions, sometimes it's very difficult and sometimes even impossible to use a graph unless you zoom very close in to find the solution to the system. So what I'm going to do now is turn this over to Steve, who's going to talk about another method called substitution for solving systems of linear equations.